Hello everyone. In today's lecture, we are going to look at a particular sorting algorithm called merge sort. This algorithm is based on the principle of divide and conquer, in which you will split a problem into smaller chunks and then will solve those chunks recursively until you have a solution. So in general, sorting algorithms have several applications. So for example, you have names and numbers in your phone book, which you want to arrange in a sorted fashion so that search becomes easier. Similarly, you may have a collection of numerical data and you want to compute some statistics on that, such as median. And again, arranging the data in an order will make those calculations easier. So today I'm going to demonstrate how this algorithm works. So the algorithm has two parts. As the name suggests, it has a merge part and a sort part. So first we'll look at the merge part, and in the second part of the video we'll look at the sorting algorithm. So for merge, I'm using some props here. So there are some just blocks of numbers that represent an array or a list of numbers for me, and this array is called A, and the numbers are arranged in an unordered manner. So my array has positions, which I call the lower bound position, the upper bound position, and so I'm counting those from 0, 1, 2, 3, 4, and 5. So my lower bound is 0 and the upper bound is 5. Okay, and my aim is to convert this into a sorted array. So as I said, the algorithm works based on the principle of divide and conquer. So let's say somehow magically we split this array into two halves, and where each half or each sublist is an ordered sublist. Okay, I'll come to that point. How did we arrive at this position where we have two sorted sublist? Okay, so let's begin here to understand the merge part of the algorithm. Okay, I also have some position pointers for each of the sublists. So the position pointers or the index pointer for the left hand side of the array begins with I, and for the right hand side of the array begins with J. And I have this empty array called B here, and my aim is to fill in all these positions in the array B with these numbers in an sorted order, and position counter for the array B is K. Okay, so how the merge algorithm works is that it will compare each element going from left hand side to the right hand side, and will compare, and whichever is the smaller element that will go in the new array, and the position counter for that sublist will move, and the position counter for the new array will also move. So we'll keep on repeating this step, and then whichever sublist uh, has a smaller element, that pointer will move and the new pointer will also move. And as I said, we'll just keep on comparing. 3 is smaller number, so this time J will move and the K will move here. Okay, again we compare I with J. This time J is smaller, so J will move and K will move as well. And now as you can notice, all of the elements from the J sublist have been exhausted. So now, since we knew that already, now all of the remaining elements from this left sublist can be filled into a new array, because we knew these were already in the sorted order. So we will just go and start filling in all of the remaining values from this sublist. So ta-da, we have this new array called B, and all of the values in this array are sorted. So this was the merge algorithm for you. So far we have looked at the merge part of the merge sort algorithm. Now let's look at merge and sort together, because in reality you will be running both the steps side by side. So let's go back to the array A that I had introduced to you in the beginning, and it has a lower bound of 0 and upper bound of 5. So we will start by splitting this array into two equal halves by finding a midpoint. So you will look at midpoint by just dividing the addition of lower bound plus upper bound, dividing that by 2. You will find a midpoint. Okay, and you split that the array into two subarray or two sublists. Okay, and then you will apply the same splitting formula to either either of the sublists, and so you will get further splitting of this sublist into smaller sublist, and you keep on doing that until you reach sublist containing single element. So we have received 6 separate sublists here containing single elements. So now let's look at the pseudocode for this part of the algorithm. So we have a function called merge sort, and we will pass 3 arguments to this function. One is the name of the array and its lower bound and upper bound. And as long as this condition of upper bound being greater than lower bound is true, we will find a midpoint, and then we'll split the array at that point. So, and then we recursively call these function for each of the subarrays until we reach the bottom of this binary tree. So for one of the arms, this is the name of the array, and then we pass lower bound and the midpoint as the other argument. And for the second array, we pass the name of the array and then midpoint plus 1, which is the lower bound for this, and the original upper bound. Okay, so like in this case, we have 0 to 2 for the left array, and 3 to 5 they are the arguments for the right hand side of the array. And then you recursively call this function until you have reached a point where lower bound and upper bound are equal. Okay, so this condition won't be true and the function will stop there. Now you can also notice that we have merge function here, which we looked at earlier. And so let's look at the pseudocode for this function now. So we are here at this point where we have these lists split into single element sublists. Now we will start merging these lists to rebuild our original array. But while rebuilding this array, we will keep on sorting our elements. Okay, so let's begin here. We are at this step. So we have 6 and 2 as our lowest leaves in this tree, and we will merge these to make a longer sublist. And when we are merging them, we'll always put the smaller elements before the larger elements. So if you remember, it's the same condition that we followed earlier in that demo video. And then with 2 and 6, we will merge the third single element, which is 5. And again, we will compare each element and then put them in the order. So we get to 5 and 6 as an ordered sublist from the left-hand side of this tree. So we apply the same algorithm on the right hand side. So we have 1, 4, and 3. So we will first merge 1 and 4 together and then merge 3 together. Okay, so in this manner, we obtain these two sorted sublists, okay, from the two sides of the tree. And this is where we began our first demo, that we started merging these two sublists into a sorted sublist. And if you remember, we just compared each element at a time and start filling in the new array in the in a sorted order. So I hope by now this pseudocode will start making sense, that we have I, j, and k as being the pointers for left-hand array, right-hand array, and the new array respectively. And each of these conditions are just comparing each element from between I and j, and the smaller one will be put into the new array called b. Similarly here, if this condition is not true, it will go and compare um, with the, like if I isn't smaller element, then it'll go to j and we'll put that element in here. And there's a typo here, should be yeah, no, there's no typo. And yeah, so after you have exhausted one of the lists, you may still have some elements remaining in the other list, and you will just fill them in one by one as we saw earlier, because those sublists are already in the sorted order. So we get this array at the end, which is a sorted array. So in summary, we applied divide and conquer approach, where we broke up our initial array into smaller subarrays, and then we merged them while sorting. And the worst case complexity of this algorithm is n log n. I hope merge and sort algorithm is clear to you, and if you have any questions, let me know. With that, I would like to thank you for your attention.